So I have refreshed to you how to find the linear approximation of a function using the Taylor expansion up to the first term, or in other words, using the derivative of a function. That's how you find the linear approximation in one dimension. Okay, so now I'm going to do it in the general case of n dimensions, and in this case this derivative will become the Jacobian matrix. Okay, so let me write it here. So in one dimensions we just saw that the way to find the linear approximation is that f of x0 plus delta x is approximately equal to f of x0 plus the derivative of f with respect to x evaluated at x equals x0 times delta x. This is how you do it in one dimension. Okay? Now, in the general case of n dimensions, we are going to write everything exactly the same, but everything is going to be a vector. So f is a vector, x0 is a vector, delta x is a vector, and the derivative is going to be a matrix. Okay? So this is how it looks like. F vector of x0 vector plus delta x vector is approximately equal to f vector at x0 vector plus the Jacobian matrix evaluated at x vector equals x0 vector times delta x vector. Okay? Let me rewrite this instead of using the bar, let me write it as j at x0 times delta x. Okay? The same way we can write the above using that notation. This evaluated at x0 times delta x. Okay, so let's do this. Let's do it for an example. So problem 5 here is saying calculate the Jacobian matrix for the function, and notice that this is a vector. It's in bold. It's a vector that depends on two variables. Okay, and this vector has two components. The first component is here and the second component is here. So this is what we would call f1 and this is what we would call f2. So the first part of the question says calculate the Jacobian matrix. So how do we calculate it? Okay, so our function f is a vector which is equal to x squared y and 5x plus sine y. And this is equal to f1, which is a function of xy, and f2, which is a function of xy. So this is the general case of having multiple inputs, which are x and y, and having multiple outputs, which are the two components of the vector f. The Jacobian matrix is simply going to be partial of f1 with respect to x1, partial of f1 with respect to x2, partial of f2 with respect to x1, and partial of f2 with respect to x2. Instead of using x1 and x2, I am using x and y. So let me change that. x1 is x, the first variable, and x2 is y, the second variable. Okay? So now I only need to calculate those four partial derivatives. And that is quite easy. So let's do it. So what is the partial derivative of f1 with respect to x? I need to do the derivative of this with respect to x. So we keep y as if it was a constant, and we will get 2xy. Okay, next. What is the partial derivative of f2 with respect to x? So I need to do the derivative of this with respect to x2, assuming that y is a constant. So it will be 5 plus 0, because this is a constant. So it's equal to 5. Next, I calculate the partial of f1 with respect to y. So what's the derivative of this with respect to y? Assuming that x is a constant. This is equal to x squared. And finally, the partial of f2 with respect to y, I need to do the derivative of this. So assuming x is a constant, this will be 0 plus the derivative of the sine, which is the cosine of y. and this is the Jacobian matrix, which is a function of x and y. Okay, so this is equal to the Jacobian matrix. And this is equivalent to having calculated the derivative for a function in 1 dimensions. Okay, this is the multidimensional equivalent. Okay, the next part of the question is, having found the Jacobian matrix, hence find the best linear approximation to the function at the point xy equals 1, 1. So that's going to be the point at which we calculate this linear approximation. Okay, remember, by comparison of what we did in 1 dimension, where we chose a point up onto which we fitted this tangent line. So now our point is not only on x, but on x and y. So we need two values. So that's why we have x0 equals 1 and y0 equals 1. So we're going to use x0 equals 1 and y0 equals 1. So to do this, we need to apply this equation here. So let's start. So f of x0, that should be very easy. We just need to substitute x0 and y0. Okay, so let me copy this equation. Let me copy it here. And now let me write what each thing is. So what is x0? So x0 is a vector which contains the point of interest. So it will contain x0 and y0, which will be equal to the vector 1, 1. Okay. What is f of x0? So that will be function f, which is here, but substituting the values of x0, so 1 and 1. So it will be 1 squared times 1, that will be 1. And here it will be 5 times 1 plus sine of 1. It will be 5 plus sine 1. Okay? So that will be f of x0. Now, what will be J, the Jacobian matrix, evaluated at x0? So we need to get the Jacobian matrix, which is here, which is a function of x and y, and we need to substitute x0, which is our point of interest. So we substitute x and y equals 1, and we get the matrix 2, 1, 5, and cosine of 1. Okay, that is our Jacobian matrix. And finally, what is delta x vector? So delta x vector is actually the vector which contains the changes in all of the variables. So this is delta x and delta y. Okay, which, if you want to write it in terms of x, this will be equal to x minus x0, so x minus 1, and y minus y0, so y minus 1. Okay, so now we can substitute here. So f at x0 plus delta x is approximately equal to this plus the matrix of the Jacobian evaluated at x0, which is this matrix, times delta x, which is delta x and delta y. And that's it. This is the best linear approximation to this function at the point 1, 1. Okay. If you want, you could substitute delta x equals x minus 1 and delta y equals y minus 1. Okay, that's fine. You can do it if you want. And that way you can write f of xy, because it really depends on x and y. So let's develop it. Let's do it like that. So let's first write this f approximately equal to what? So this is going to be 1 and 5 plus sine of 1. And now let's do this matrix product multiplication. Okay, so this will be a vector, a column vector, whose first element is 2 delta x plus delta y, and the second element is 5 delta x plus cosine 1 times delta y. Okay, So if we now add those two vectors, this is equal to a vector with 1 plus 2 delta x plus delta y as the first element, and a vector with 5 plus sine of 1 plus 5 delta x plus cosine 1 times delta y. So you can see that we have arrived at a function that has two outputs. But this is a linear function because it depends, in a linear way, it depends on delta x and delta y. It doesn't have any delta x squared, it doesn't have any cosines, unlike the original function that had squares and had sines and so on. This approximation does not have any of that. It only has linear combination of terms, okay? Either constants or simple delta x and delta y. So this means that if we are interested in finding values of this function very close to the point 1, 1, we can instead use this function, which is much simpler and easier to calculate. For example, particularly if we were using a computer. It's all linear operations, and it's a very good approximation of that function near the point 1, 1. Okay? If we want to do the substitution that delta x equals x minus 1, or let's write it more generally, x minus x0, which in this case is x minus 1, and delta y is y minus y0, which in this case is 1 y minus 1. If you do that substitution, you arrive at a function in terms of xy, which is approximately equal to, so doing that substitution, you end up with minus 2 plus 2x plus y, and here you end up with 5x plus cosine of y times y minus 1, and then plus sine of 1. Sorry, it's not cosine of y, it's cosine of 1. Okay? So these are constants. You shouldn't be scared about this cosine and this sine because it's just a constant. So as you can see, this is clearly a linear function of x and y added to some constants. Okay? So that's it. That's how you can write the best linear approximation to a function f around a given point using our equation. I hope that was clear. Thanks for watching.